Hello, my name is Vries and I work at Eslon in the Netherlands. In this presentation I would like to show you what was done and found during the first EMC test on the first version of the LYSA QPR unit. Let's start with EMC. This abbreviation stands for electromagnetic compatibility. Electric and electronic equipment can cause electromagnetic or magnetic fields during operation. These fields can affect other equipment in the neighborhood. Equipment causing the EM fields is called the aggressor. Equipment that's susceptible to the EM fields is called the victim. Equipment is usually only aggressor or victim, but it can also be both. In the worst case, equipment is the victim of its own aggression, but then it was designed by the wrong engineer. There we have the QPR. This is the Quadrant Photo Receiver. The QPR will be mounted on the focal plane in the laser instrument. It will receive the light of a laser beam, convert it into electric current and condition the received signal so that it can be processed well by a phase meter. The picture on the left of the slide shows the complete QPR mounted on a large metal block. The picture in the middle gives an intersection of the QPR box. The vertical green line on the left represents a printed circuit board that contains the sensitive electronic circuits, and the smaller vertical green line is a PCB that holds the quadrant photodiode. That's the receiver of the laser light. The laser beam enters the QPR box from the right side. What's inside the QPR? The picture on the right shows us a block diagram of the circuitry inside the QPR. On the left we see a circle with 4 segments. This is the photodiode that receives the laser light. On the right we see 4 circuits that convert the current from the photodiode segment to 4 output voltages that will be sent to the phase meter somewhere else on the satellite. There's also a temperature sensor mounted in the QPR box. The design of the recently tested electronics was done by Fernã's Barranco at the Albert Einstein Institute. The received laser light will be very weak. Therefore the QPR is very sensitive. This makes the QPR highly susceptible for EM or M fields. The QPR doesn't transmit strong EM or M fields itself. It will not act as an aggressor for other equipment. The goal of the EMC test is to discover if the QPR, including its cabling, is susceptible for electromagnetic fields. Give it a measure and find which improvements will be required. The measurements are performed at ESTEC in Noordwijk. The picture on the right bottom shows a typical EMC test setup at this facility, with a red transmitting antenna and the QPR placed on a table in front of this antenna. The EMC test was supported by Laurent Tronon and Dongsheng Zhao from ESA. Design and production of the QPR housing, as well as facilitating many other aspects during the EMC test, was done by the NWO Institutes NICHEF and Esron, with contribution from NICHEF by Niels van Bakel, Guido Visser, Trino Hoofd and Michel Naafs, Robin Cornelissen, and contributions from Esron by Martin Frericks, René Wanders and Ette Vries, and probably some others that I've forgotten, sorry for that. So why do we expect EMC problems? Here on Earth the environment is filled with smartphones and other terrible radiating equipment. In space you won't encounter them. On satellites, however, there are also radiating apparatus that may degrade the fine qualities of the QPR or even block out all of the functionality. Think of equipment like telemetry transmitters, actuators, antenna systems, power and logic controller equipment, leaky cabling of the equipment mentioned before. Their signals can couple into the QPR cabling, causing currents inside the QPR box that disturb the performance of the QPR electronics. These are usually signals with frequencies below 1 GHz. If the QPR housing appears to be leaky, signals with higher frequencies can enter and disturb the QPR performance. What may happen if disturbing signals enter the QPR, and how can these effects be measured? There are 3 effects that can occur. They can all be measured by monitoring the signal at the outputs of the QPR. When no laser light signals are applied to the QPR, the outputs are expected to show a kind of steady North floor over the frequency spectrum. Disturbing signals can cause tones to appear in the spectrum. Signals can couple in directly when their frequencies are inside the working frequency band of the QPR. Modulate signals outside the working frequency band can cause demodulation inside the QPR, causing tones. Even tones from an unknown source, called spurious signals, may show up. Undesired tones in the frequency spectrum limit the QPR performance. We want to monitor more channels simultaneously, so a high-performance 4-channel oscilloscope with a fast Fourier transform option is the ideal equipment to measure this effect. The two graphs shown are live from the tests at ESTEC. The second issue that may be found is rising of the noise floor while applying the disturbing signal. A rising noise floor limits the QPR performance. Measuring this effect on only one channel was assumed to be enough. Therefore, a spectrum analyzer was chosen because of the good sensitivity of such equipment. The graph added gives the normal noise floor of the QPR in black, and in blue the rising noise floor due to interfering signal injection. A third effect that can occur is drifting of the DC level at the QPR outputs while applying disturbing signals. DC shifts can limit the performance of the QPR or even block out the complete functionality in extreme cases. The DC shifts can easily be measured with a set of DC voltmeters because the QPR outputs are DC coupled. And now the EMC test plan. The measurements can be divided in two groups, conducted and radiated. Conducted EMC measurements are done by directly injecting the disturbing signals into the QPR cabling. Then measure what happens at several frequencies. See for the plan the left side of this slide. Conducted measurements can be split in three groups. Disturbing signals are injected in all power and bias wires at the same time. This is called bulk cable injection on the power and bias lines. This is a common mode test and it's performed in the frequency range from 50 kHz to 100 MHz. See the orange colored region. Disturbing signals are injected in all coaxial signal wires at the same time. This is called bulk cable injection on the coaxial signal lines. This is also a common mode test. It's performed in the frequency range from 50 kHz to 100 MHz. Also see the orange colored region. And then disturbing signals are injected in a single power or bias wire. This is a differential mode test performed in the frequency range from 50 Hz to 100 kHz. See the blue colored region. Please notice that there's a slight overlap in frequency. On the right of this slide, the test plan for the radiated EMC test is shown. Radiated EMC measurements are done by producing a well-defined electromagnetic field around the QPR setup using antennas for radiation and an RF probe for monitoring the field. 3 different antennas are used to cover the entire frequency band. The used frequencies and signal levels are mostly derived from preliminary requirements, but at some points also dominated by limited facility system properties. So, what did we encounter? Here one of the results. Showing all the results of 4 days measuring will take too much of your time. The subject of this test was bulk cable injection on the coaxial signal lines. Without disturbing signals, the blue curve in the graph was measured. This is the noise floor of the QPR that's used as a reference to compare the test results with disturbing signal injection. Applying the disturbing signals resulted in what is shown in the black curve. Ideally the blue and the black curve would have looked the same, but as you can see there's quite some signal leaking into the measured frequency spectrum. This didn't come as a surprise, luckily. From the design it could already be derived that such a signal leakage would show up. This was the same for all the other results. It's clear why things go wrong, and it's also clear how to improve the QPR to make it perform better in a noisy environment. The test results led us to 4 groups of recommendations. First, the power and bias lines of the QPR require better filtering for high frequencies as well as for low frequencies. And second, the coaxial signal lines from the QPR require filtering for high frequencies outside the QPR working frequency band. How to cope with frequencies inside the QPR working frequency band is subject of investigation. 3. The PCB layout of the QPR electronics require improvement. Disturbing signals can reach the sensitive parts of the electronics now, and this should be avoided in the next version. At last, the metal housing is leaky for very high frequencies. Several improvements of this mechanical part are suggested, equaling better connectors, gasket, a lower bolt-to-bolt spacing. So far, this quick view into the EMC test, the test results and the recommendations. Thanks for your attention.